Okay, I think we can restart the session before we go for lunch. I hope you had a refreshing break. And we had the project officer with us. Now the floor is yours, Alvise, for the synthesis and processing presentation from MBN Nanomateralia.
My speech today wants to go through one of the main steps of bringing the tetrahedrite into the thermoelectric generator. So we saw before the break all the raw material sourcing, and now it's time for the material synthesis. And later on, we will learn more about the material consolidation, manufacturing, and the final assembly. So as regards the material synthesis, I want to talk about why we choose ball milling, why is MBN involved in that, and how this transformation from mineral to thermoelectric material can be done, and how we eventually did it. So the ball milling is a technique which is quite present in all the universities because it's quite simple. It's based on the fact that when you smash materials together, they tend to fracture, to break, but also to weld together. And after a certain repetition of these events, you start having one material folded into another to disperse oxides or brittle materials in soft matrices, and in general to create a quite specific nanostructure that improves the materials. In most of the cases, improves the mechanical properties of the materials. But there are different ways of running the ball milling. You want to do the fracturing, you try a different setup of the plant. If you want shear, fracturing is another one. If you want pure impact, you are more leaning toward the alloying effect. So there are different alloying systems all around. Some are more leaning toward the grinding effect, and some other more leaning toward the mechanical alloying effect. So throughout the presentation, you will see this tumbling mill going around, but we never used it actually. It's just there because it's the more clear reference to a ball mill that we can have. The vibratory mill is more like a shaker, so the energy of the impact is higher. The planetary mill is rotating in a couple of ways, and it's somehow limited from to the energy. It's limited by the centrifugal forces. The attritor mill, due to its shape, is more used for grinding, and the effects is not only due to the equipment that you are using, it's also due to the kind of material that you are putting inside the ball mill. So if you have ductile systems, you try to you tend to make them flatten and fall one into the other. Brittle materials are instead going to break down into smaller and smaller pieces and ends up in between the ductile ones if you happen to put them together. Or you can end up in a completely fine dust if you just have purely fragile materials. So the typical structure that you can achieve are sort of these ones. You can see on the top standard image from textbooks, and on the bottom something that we collected at different stages of ball mill when you have elements that are starting to blend one into the other, and after a prolonged ball mill, you have a sort of soup of elements all together that is quite effective in starting any possible reaction between the elements. So the dispersion is one of the effects, and the other effect is the reactivity. When you put together elements that are thermodynamically favored to combine into intermetallics or ceramics, they do that. So basically, for example, putting together titanium, aluminum, and carbon, we end up with the titanium carbide in an aluminum matrix. And similarly, iron oxide and aluminum, it's a thermitic reaction that can be activated by a ball milling also in smaller quantities, so without melting down all our equipments. And this happens also for tetrahedrite. We put together elements, and thanks to the thermodynamics of the system, the ball milling deliver us with the tetrahedrite phase, which is quite complex. We cannot, with ball milling, try to achieve that if it is not thermodynamically favored. But if it appears in nature, it means that somehow the thermodynamics is going into that direction. Yeah. So the problem is that in nature, the tetrahedrite is not only copper, antimony, and sulfur. There are also other elements that we need to tackle with that, and we will see later how this is sorted out. So you can argue, is this the best techniques to do this job of putting together elements? Since, as I see, if there is not a thermodynamic drive, this is not going to happen. Well, there is another good reason for ball milling, for using ball milling. The other reason is basically derived from the origin of ball milling. The idea for ball milling was to avoid the sliding of and the movement of dislocation by increasing the number of grain boundaries in the material. As we have seen, it is quite effective in creating the nanostructure, and this nanostructure is blocking the movement of dislocation. This was the first good application for ball milling on metals, because it was creating more grain boundaries, blocking dislocation, adding also some nanoxide here and there that blocks the further growing during annealing of these metals. And these structures are, or this combination of the effects, are those that we are using also to produce some of the elements and some of the products that we have by combining immiscible metals, having compositionally complex alloys, or by creating cermets, and of course by creating nano dispersion of oxides into alloys. But although this seems to be not pertinent to the thermoelectric system, this is also, the nanostructure has also meaning for the thermoelectric system, because the abundance of grain boundaries is helping in the thermoelectric effect in reducing the thermal conductivities, while the electrical conductivity is well kept. So you can imagine the thermoelectric material as having this capability of a slight difference between the thermal conductivity and the electrical conductivities, and then the cloud of carrier, of electricity carrier, is different in the two ends of the material, the cold and the hot side. If we do the ball milling, we increase the number of grain boundaries, so we have even more this difference between the two sides of the material. And of course, if we have a p-type and n-type materials, we end up having on the cold side a higher concentration of two different energy carrier, and these two combines, and we have the thermoelectric effect enhanced by the nanostructure that is somehow decoupling the movement of heat and the movement of electrons. The complexity of the thermoelectric effect is quite a lot. Later we will hear about the properties of these materials and the meanings of all of these contributors, like the thermal conductivity, the Seebeck coefficient, so the intrinsic material properties, and also the overall structure contribution. But yeah, this is the second reason why we choose the ball milling, to have a direct formation from the elements and also the nanostructure. Combining these two, we can aim to have this thermoelectric materials from tetrahedrites. So why NBN? Well, it's simply we have a long experience on ball milling. We started doing this on 30 years ago. We have a long history of trying different materials and applying ball milling to achieve different effects. The company histories goes back, as I was saying, 30 years. During this time, we touched many different material systems, also thermoelectric, although most of the production nowadays is leaning toward thermal spring materials for automotive, ODS materials, and also green cements with alternatives to tungsten carbide. We based the company on our own design of ball milling, which is a hybrid of what I showed before, and we use that at different levels of productivity, so we can scale quite easily from lab to industrial scale. But making the material is not the only thing that we have to do to deliver this to the market. Is also the ability of do processing. For example, after the pre-alloying or the ball milling, in some cases we need to have heat treatments in order to achieve a specific alloy microstructure. And similarly, according with the downstream consolidation processes, we need to control the morphology of the powder in order to facilitate the consolidation into pieces. So it could be additive manufacturing, or could be thermal spraying, cold gas spraying, hot pressing, SPS. As regard the project start, we are heading toward SPS. And also we are taking advantage of the thermal cyclone that inevitably the material is having during SPS to avoid this thermal treatments. So our materials are going directly to the ball mill and from the ball mill to the SPS. There is a bit of morphology control, but we will see it later. So I was mentioning the product range before. So most of it is powders for diamond tools, metal binders in this case, or titanium, biomedical grade titanium, ODS, and special mixture of iron, aluminum, manganese. These are not alloys. These are a mix of elements for the powder for braking pads. And downstream, we have all these techniques, as I was mentioning before, for powder consolidation, extrusion, and thermal spraying. Being on this so early in the value chain of product development, we also have to provide to customers and to ourselves in most of the cases, some hints on how the materials behave once consolidated. And that's why we have also in-house some prototyping facilities for doing that. The hot and cold isostatic presses, some current-assisted hot press, which are not like SPS, but the closest thing that we have, cold presses and batch furnaces, and some capabilities, of course, for characterization. So this completes the overall view of wire ball milling and wire ambient. So let's look how it can be done. So there has been a lot of work at the beginning of the project in the first, second year in order to try to identify which is the optimal composition for the tetrahedrite. The tetrahedrite structure, as we are seeing here, is quite specific, but the copper sites can be substituted by many elements. I highlighted here chromium, manganese, cobalt, nickel, well, all the first row there of transition metal, but there are more. And on top of that, there are elements that in nature are included in tetrahedrite, and we are not really needing them, like arsenic or I think bismuth. Sulfur can be also substituted by selenium and tellurium in nature, not something that we want. In any case, from initial experiment, DOE, design of experiment that included most of these elements, and also from DFT calculation, we identified iron and zinc as best substitutes for our purposes. And this was the target composition that we had from year 2 onward. On this composition, we need to fit in the tetrahedrite from the actual mineral. In any case, we started working on this composition, and we identified from the first trials a problem that tetrahedrite is not the only structure that is formed during the ball milling. Ferritinite is forming too. Luckily, ferritinite tend to disappear after prolonged ball mill, as we can see here from the XRD peaks. There is those that characterize the ferritinite that are decreasing over time, and everything is turning into tetrahedrite. This is also boosted from the iron and zinc themselves. They are not only boosting the thermoelectric properties, they are also boosting the capability of the ball milling to deliver tetrahedrite instead of ferritinite. We can see, for example, here there is these peaks. These double peaks are due to the absence of iron and zinc. In those cases, no matter what is the timing of ball milling, we always end up with both ferritinite and tetrahedrite. So iron and zinc were pivotal in creating this only tetrahedrite structure, mostly. In any case, we cannot simply grind the ore and pretend that we arrive at the end with working thermoelectric materials. It's almost thermoelectric because minerals are always different, and this target composition that we have is basically never present in nature. So we need to add the dopants, add the iron, the zinc. In some cases, we tried also with nickel, and compensate our addition with for the sulfur and antimony. Doing this is effective. We have seen it. The dispersion of elements is going well. All the sulfur is where it should be, iron too. But we also find arsenic and silicon oxide, and these are elements that are coming from the mineral. And we try to identify which is the way to get rid of these oxides, but eventually we realized that we have to live with it and try to adjust the mineral to synthetic ratio in order to minimize the potential negative effects of those phases. So these are from the early examples of mechanochemical synthesis, where we had powders from minerals from Neves Corvu. In that cases, the presence of quartz and pyrite was quite a lot, and we saw that in all the systems, and also in all the milling condition that we tried. But that was deciding for trying to compensate for this composition in order to have a final thermoelectric materials according with our target. And the approaches that we kept are basically three, the route that we tested. One is the simple addition of synthetic tetrahedrite to the mineral. So we know that the mineral contains iron and other elements that can provide the thermoelectric effect and boost also the formation of tetrahedrite over fermatinite. So one simple idea is to make pure synthetic tetrahedrite and then mix it with the mineral. Mix it with the ball milling, but still mixing. The other idea is to do a sort of combination, just putting these elements not as tetrahedrite, but simply as elements, and then do the ball milling. And this way, we can arguably skip a step of formation of tetrahedrite or a master for dilution. And the third step is a correction of the composition, which is a bit more intriguing from the point of view of the technology, since we have to closely look to the composition of the mineral. For example, in this case, the mineral was from a rose lava mine. And in these cases, the amount of iron was still above the needed from the theoretical composition. So adjusting the proportion of target to mineral, we can fix that quantity of iron, ideally, and then looking into the other elements, put them back into the composition, considering where they are going to end up in the structure of the tetrahedrite. And finally, adding just the elements that are needed to arrive to the theoretical final composition, which is really interesting as an approach. But then we realized that the best option is to just go for a mixing of synthetic and mineral. And why that? Because the information on the mineral is not telling the whole story. The iron is not always available for tetrahedrite formation. In some cases, it's just blocked into pyrite. And different techniques deliver different values of the composition. And at the end, there was a burden of characterization that was not matched by the improvement of the material. So we stayed with this approach of simple addition that we tested at composition ranges between 820, 50, 50, 20, 80, ending up in something in between around 30% of mineral. So eventually we did exactly in this way, choosing the addition. We tested also correction because we also did that, and we saw eventually that the better option was to just make the synthetic tetrahedrite and then ball mill it with the mineral. We used the equipments at all scales, from lab scales delivering a few grams per batch to pre-pilot. In this case, we were delivering 200-300 grams per batch. And in the pilot, we start from 1.5 kilos up to 10 kilos per day. The final loop of processes was including the formation of the tetrahedrite precursor via ball milling, then the addition of the mineral to perform the final alloying, a sieving process in order to remove all the coarse powders that are not suitable for the SPS process, and those coarse powder can be eventually reused in the ball milling and looped back to the sieving in order to maximize the yield of the process. The final composition that we have is the closest one that we can get to the target properties. And at this stage, we still are in the powder realm. Still we need to have the consolidation process, and the assembly of the thermoelectric is still a long story from this point onward. But this, up to this, was our role in the project, and I want to thank everybody for this journey from the beginning 4 years ago up to now, and open for questions.
Thank you very much, Alvise, for a very nice talk. Are there any questions? Yes, one from.
Okay, thank you very much for the nice talk. I actually mainly two questions. One is, what is the, let's say, the scalability of the process at larger scale, at 10 kilograms per day? What do you think you could reach at large scale for this process, with this kind of materials?
Yeah, definitely. I talked today just about tetrahedrite. That was the easy part to some point of view of the materials development. The more problematic material is the N-type. We were using magnesium in that case. So in that case, all the processes are more or less the same, but everything is more prone to get on fire. So the scalability on the magnesium antimonide is something that we can do. We are used to work with pyrophoric material like titanium. For the tetrahedrite is even more simple. We have production capacities. I talk already just about pilot and pre-pilot, but then we have the industrial machines that are delivering about hundreds of kilos per day of material, based on the density of iron. So, but that is the volume.
Okay, thank you. And related to that, how do you deal with, let's say, atmosphere and oxidation during the process?
But again, for tetrahedrite, it's not much of a problem. In any case, we do the ball milling in argon, and we do the handling of powder under nitrogen. Then it is sealed and then is shipped to Genicor. They have a glove box to handle it, and then it's sintered. So the problem is not much there. In any case, it is exposed to air in some of these steps, and it's pyrophoric, the N-type with the magnesium antimonide, but it's not self-igniting. So we just keep it under a sort of protective gas flow, and that's it.
Thank you.
Alvise, so we never really proceeded in that direction. But regarding the pyrite, would it be possible in the future to combine some sort of heating the mineral to convert pyrites into pyrotides and then do the mechanical in some sort of an integrated process? Would that be something you would
Well,
envisage?
different steps that we can accomplish internally in the company, yes. Not everything in one step. But we could do a thermal treatment to somehow degrade the pyrite, and if it is melting now in a block, we can break it with a jaw crusher and then use that as a starting raw material for whatever other materials.
Okay.
Thank you very much, Patricia and Geoffroy, for the contribution. So if there is no more question, as Alvise said, the next step for the processing of the material is the SPS consolidation. So for that part, we have Marcin Rosinski from Genicor, another partner of the START project, who will give a presentation on this part of the processing. And this will make our last talk for the morning session, and then we will have lunch. Yes, Bruno, it will be here. Yeah.
This is a.
So you have to.
Good morning. Okay, today I will present Genicor contribution to the START project in the field of spark plasma sintering of tetrahedrite-based compositions by Genicor's technology UFAST. UFAST is upgraded filter-state sintering technology which use high current pulses to heat material, mainly powder, during the sintering process. Specific feature of this technology is quite short cycle time, very often below 1 hour, with annealing time a few minutes at the sintering temperature. This technology enables high densification at solid states, relatively low sintering temperature, and limited grain growth. UFAS is a platform for also scalable platform for thermoelectric manufacturing. Here we see different type of the devices on the left. The smallest one, compact device, which fits to the samples of size from 10 to 30 millimeters. Next one is GC model, which we use for START project for making elements up to 85 millimeters. This is UFAS, it's scalable technology platform. The last one is UFAST mass device, 6 meter length device with different 3 chambers, where each chamber is dedicated for different stage of the process, like degazing, sintering, and cooling. Degazing for 1-2 samples, it's not as crucial, but with increasing the amount of the powder with the total surface area, it's noticeable bigger collecting of the gases because of the surface of the powder is as big that sometimes the degazing took longer than whole SPS process. And the same last one, cooling stage, because it's also important stage of the sintering materials at, for example, tetrahedrite materials which are quite fragile. This is why incorporating specific cooling rate, specific annealing stage is also important to achieve not high density but high yield from the process to limit the cracking of the material. Genico, it's developer of this UFast platform. We have quite well equipped laboratory with the presented previously devices. We have experience in the collaboration with leading research institution and industrialization of R&D application through starting projects by joint development agreements processes, finally of producing in small and bigger batches samples. Joining the START project was natural choice because we believe in actions aligned with the European Green Deal, which not only benefit the planet but also bring tangible advantages to our company. This project allows us to participate in creating innovative technological solutions that reduce industry's negative impact on the environment. Our role in the project starts from the making green pellets on the base of powders, which we achieved from MBN project partner. After that, making the technology of sintering samples, and finally making technology of near net shape sintering. A lot of work has been done at the beginning of the project through the first 2 years. That a lot of different composition what Alvise presented were developed, and there is no, unfortunately, one way to sinter any type of the material, and the same like small deviation composition in the powder generate some problems for MBN, the same in Genicore case, because we have to, through new delivery of each new batch, we have to redefine the sintering parameters to achieve the same properties. It was initial stage of the project, but this presentation covered the final results, where we finally scale up the process and we delivered to our partners ready to integrate elements for tech modules. In R&D study and production process, the UFast GC model have been used. The maximum heating power is 100,000 amperes. Maximum size is 85 millimeters diameter. Of course, other geometries are possible. The process can be operated under different level of vacuum, low up to 10-5 millibar. Device is equipped with thermomolecular pump. Also, additional gases, if would be needed, like for example, argon, can be used as a atmosphere in the process. Device can be used in different ways. At R&D process, technologies are responsible for the writing the proper sintering path, where the operator step by step incorporating the parameters on real time to the machine. But at the production stage, we base on some previously generated recipe, and the machine automatically conduct whole sintering process. It means that the only task for the operator is put the system graphite set into the vacuum chamber and press start button, and parallelly spend time for the assembling process of the next set. Typically, sintering processes are conducted in graphite dies. During the process, temperature can be measured in different way through the hole in the pressing stamp by pyrometer, which give us information about almost real temperature of the sample, because the distance between the sample and the point where the temperature is measured, it's a few millimeters, or on the bottom part of graphite die. Here we have a few examples of different round geometries, 20, 30, 40 millimeters, and using this geometry were applied at the beginning of the process, project, but other geometries also possible, with the aim to save powder, save time, and finally money on the additional steps of, for example, cutting the round samples and additional processes. Here it's look from the view from the vacuum chamber. Temperature is measured from the parameters which are placed here. The typically process look like the first step is putting the powder into the graphite die, making some green pellets. After that, putting the set into the vacuum chamber, heating with the specific profile of the current temperature, profile of the load, sometimes incorporating of the additional stages at the heating. Very often we use some low temperature annealing to remove absorbed gases on the surface with the aim of increasing the final density of the material. And this stage takes around a few minutes. When we have full operational vacuum in the chamber, we can go further with the heating, and the same at the cooling stage to limit the cracking. Example of near-net shape manufacturing capability. It's connected with the designing process of graphite die, punches. We have a CNC machine in-house. This is why we can quite fast prototype, changing the design of the dies and stamps to achieve high temperature uniformity of such a system, also increase, for example, lifetime of such a system. As I mentioned, not only the sintering process is crucial, but also cooling stage. Here is an example of different yield from the process in relation to the cooling stage, which is divided on the cooling with specific rate. Finally, the cooling of order 15 Celsius degree per minute were applied, and additional annealing stage around 300 Celsius degree. Technology is scalable, not only scalable through the machine designs, but also through the graphite die design. Here we see the idea how it can be proceed. At the moment when the technology of sintering one-hole system is developed, we can go to the stage 1 when we design multi-hole graphite die. At this stage, important, it's mentioned uniform temperature distribution, and also we have to take into account that the graphite die must withstand the load, and very often the thickness of the wall it's lower than the initial stage. Of course, using the bigger system with bigger mass, higher amount of the pressing stamps, unfortunately it's necessary to redefine the sintering process, because we have bigger bigger volume of powder, we have bigger mass of the graphite dye. But from the first stage, we have a lot, like what should be a load, what should be heating rate, annealing temperature, and etc. At this stage, we use quite the same parameters, in the meaning that if for the one whole system heating rate was needed of order 50 Celsius degree per minute, and current intensity was 1 kiloampere, it means for the system we have to increase only the pulsing, we have to increase the power of the heating system. The same with the load. We count, of course, the total surface of the pressing system, and if we had, for example, 50 megapascals and the load was, for example, 2 tons, we have to recalculate it and use 10 tons. Yeah, this is why it's not completely new situation, but we can rely on the achievement from the first stage. The next one is incorporating additional layers of the material being sintered step by step, second one, third, and etc. Maximum what we have in our production is 5 layers, where almost 65 elements in one process can be produced. There is some limitation, for example, the size of the vacuum chamber or total of total height of the pellets we put into the graphite die. And here we can see the graphite die for the square elements 23 and 23 millimeters with thickness 2.7 millimeters, with some small shiftment of sintering temperature. Material were fully densified. We reduced the cracking by the temperature optimization at the cooling stage. Temperature is measured through central hall of the system. To increase the lifetime, some graphite foil can be incorporated to limit the stacking of the powder to the graphite, and oppositely to limit the carbon contamination from the graphite dye. Other materials that foil can be also used. At this stage, when we are incorporating to multi-level system, it's important to use exactly the same thickness of the green pellets, because the system must withstand, pressing stamps must withstand the load which we use, force which we use. You can imagine that if only one leg will be higher, probably at the applying of the load, the system will be destroyed because the too high load to the compressive strength. Material, it's quite brittle. This is why additionally we developed or made some special holders for the samples for easy shipping of the materials. This is a 3D printed material, and the same graphite dye can be quite universal. The dye were designed to fit requirements of making bigger cuboids and thin layers, with intention don't lose time for the further development of different geometries. Thickness of the cuboids can be modified simply by the applying of a specific amount of the powder, and this geometry was optimized for slicing into multiple legs. Other approach were thin legs with the thickness 2.7 were produced. Finally, the deviation of the thickness can be optimized through applying some spacers, where instead of the graphite foil, which is quite weak material, graphite spacers can be incorporated. It such an approach improve the parallelism, limit the roughness of the surface, but of course, because of the thickness of graphite, separators influence on the effectiveness of the using graphite die, because the total height of such a system increases. Maximum up to now 3 years of tetrahedrites were produced. Some thermoelectric properties of materials, power factor approaching 2 milliwatts per meter Kelvin, ZT almost 1.2, and here we see holders for the making cuboids, and here four holes, 3-layer system for making 12 elements, and the same. They can be transported as a system without slicing of the pellets after the process, but additionally we can, using simple knife, we can split them. To limit any risk of oxidation and contamination, the U-fast machine can be combined with the glovebox system. This increase process reliability, extension of also technological capabilities. Some conclusions. U-fast technology was validated as a proper technology for the manufacturing of TE materials. Surprisingly, we achieved better results for scale-up materials, where instead of sintering in one hole, we sintered 12 elements. Still, we don't know what the factor of the process is responsible for this. Maybe a little bit different cooling stage because of the bigger mass of the system. Some numbers: over 1,300 samples were consolidated through the process. We heard about the kilograms, which is around 10 kilograms sintered materials, probably around 30 different compositions. At the beginning, the first part of the project, we were a partner of delivering material from R&D stage to LNEC and Sintef, and finally we scale up process to be partner to our technological partners like technology and RGS. And the team, because always behind the results are people. Thank you. Thank you very much.
Thank you very much, Marcin. I think we are almost done for this morning, if there is no other questions. And we can have a break for lunch next door. Thank you very much. And then we will continue after lunch with a nice presentation from Patricia, as usual. So, yes, you can go now for lunch. Thank you very much.